Good morning, everyone. I'm David Potyandi from ITASCA. And as we always say about having the honor, I have the great honor and pleasure of introducing Martin Schöpfer. He's a little worried about what I'm going to say. He doesn't know what I'm going to say. And I'm not like Peter Kundal. I'm not going to give just a one sentence thing. But don't worry, Peter, it won't be too long. So we'll begin. Undergraduate degree in, as he says, pure geology in 2001 in Salzburg. Decides to go to University College Dublin. So he's this geology guy, and somehow they was said, oh, there's this particle flow code. Maybe you can apply this to modeling faults. And so, as he says, he got thrown in the deep end. While he was doing that in 2002, he went to the first International PFC Symposium, and that's how he kind of became connected with the ITASCA family here. Finished his PhD in 2005. Then he spent 7 years as a postdoc and independent researcher, continuing to look at applying PFC to different structural geology applications. He went to University of Vienna in 2012, where he's now a docent, where he can supervise PhD students and teach. So now I teach a PFC course, and in my course, I do a lot of goofy things with balls and stuff. And then I get to a point and I say, look, this isn't just a bunch of fun and balls. People also apply this to science. And I use Martin as an example. Some years ago, he sent me, this big set of slides, 13 different scientific applications, 17 journal papers. And so again, I use that because I see Martin as an example of someone who's like a real scientist who's applying PFC to gain deeper insight into these things. Now a little story. Back in 2007, he was a visiting scholar at the University of Minnesota. And so in the evening, we went to a bar off campus. And of course, him and I being ourselves, we both brought our laptops, and we go to the back of the bar and it's smoky and we're drinking beers and we're looking at our laptops and we're showing all this stuff. And the waitress keeps saying, looking at us after about, an hour, she says, what the heck are you guys doing? And so, we kind of look at her and say, do you really want to know? And so then we proceeded, to show her what all these things are, right? Now, in that interest of this idea of that this is fun and we're trying to learn things about this, I'm going to close here with a quote from Isaac Newton. And it's a quote that he gave looking back on his life, okay? I do not know what I may appear to the world, but to myself, I seem to have been only like a boy playing on the seashore and diverting myself and now and then finding a smoother pebble or a prettier shell than ordinary. All the while, the great ocean of truth lay all undiscovered before me. So with that, I'd like to introduce Martin, who's going to tell us of all these sorts of interesting things about fractures, and maybe we'll uncover a little more of that ocean. So please welcome Martin Schöpfer.
Well, thank you, Dave, for this very nice introduction. So that's 5 minutes less of speaking time already. All right. So thank you very much. And thank you for the award. And I thought I'm not just going to talk about the topic of the award-winning paper, which is drilling-induced tensile fractures. I want to give you a bit of a wider overview of the sort of modeling I've been recently doing using rigid blocks to study breaking rocks. And I'm going to cover 3 topics: drilling-induced fractures, faults, the reactivation of faults due to poor pressure changes, and I'm going to finish with the hot topic, namely calderas and the caldera collapse. Right, so let's get started with the team. That's myself and the co-authors with our Stegosaurus. That was an animal that lived during Jurassic times, and the Jurassic is an important period in time. What's nicer then? No mankind, no politicians. It was good. Right. No, it was really important then because there was a vast sea, an ocean covering majority of Europe, and there were clays being deposited in the area of what is nowadays Switzerland. And It is this Jurassic Opolinus clay formation that the Swiss decided is the ideal rock formation for the long-term storage of the radioactive waste. So there were 3 areas selected in northern Switzerland, and ultimately the central area, Nördlich Legern, was selected to be the best site based on geology. Now, you don't make such a decision easily, obviously, and there was a lot of drilling. Most of the drilling was actually cored, and it's a really excellent data set because, as you will see, they have image logs, they have the cores, and they did a 360 degrees core scan. So you could see the core, the rock formation, and you also had then the image log. On top of that, they did a vast amount of rock mechanics tests. So for every formation, it's the rock mechanical properties are really well constrained. So it's the ideal kind of data set you want if you want to model and to better understand drilling-induced fractures. And this is one of these classic examples with the so-called centerline fractures. This is the borehole image. And you have here this drilling-induced tensile fracture. And this is here the 360-degree core photo unwrapped. And you see there's no fracture in there. So this is an absolute clear example that this centerline fracture must have been drilling-induced. It's not a natural fracture. And you all know the reason for that. It was Kirsch, an engineer who first derived the solution for the stress perturbation around a hole. And it is that stress concentration here, which is located parallel to greatest horizontal compressive stress direction. This is where you can initiate tensile fractures. So to have a closer look at the conditions for tensile fracturing, I'm plotting here what is called a stress polygon. It's a bit of a busy plot, but effectively it's a more Coulomb condition, plotted in a plot of maximum horizontal stress versus minimum horizontal stress. And then you can map out possible states of stress in the Earth's crust. And you assume that the Earth is critically stressed in the so-called Rankine limit state. And then you can map out the areas where you have a normal faulting tectonic regime, strike slip, or reverse faulting tectonic regime. So this maps out the possible states of stress that you have in a critical stressed crust. And then there's the Hobart-Willis criterion. So he used Kirsch's solution to derive a criterion for the onset of fracturing. And then you can take this criterion and plot it as a straight line. For example, for a tensile strength of 0. So all the stress states above that tensile strength of 0 line, this is where tensile stresses develop. Okay? And then it obviously depends on the tensile strength of the host rock if you form a fracture. So as I said, strike slip is a really good stress regime to get drilling-induced tensile fractures. Why? Because the maximum differential stress is in the horizontal plane. And what is going on in the area where the Swiss decided to deposit their radioactive waste? Well, it's a dominant strike slip regime. This is very common in active mountain belts, that you either have a strike slip or reverse faulting regime. And this is the reason why in many of these image logs, drilling-induced tensile fractures can be formed. So this is regarding the initiation of these drilling-induced tensile fractures. What about the propagation? And if we want to look at propagation fractures, we need to look at linear elastic fracture mechanics. And luckily, there's a solution, an approximate solution for this particular problem. So you have the drilling mud, which exerts a pressure within the borehole. And then you get these fractures developing. And then you can assume, okay, this drilling mud enters these drilling-induced tensile fractures. So you have a crack pressure. You have a remote stress field, which you define. And then you can solve for any sort of crack length, the stress intensity factor. And for given crack lengths, you also then can solve for the crack aperture. And I'm showing this here plotted these equations. So this is the stress intensity factor as a function of fracture length. And on the right-hand side, the fracture aperture. So what it shows is that you just need a tiny initial flaw, and then you get sudden fracture propagation until you hit the stress intensity factor line there. And then if we say, okay, now we increase the density of the drilling mud, the pressure in the borehole, what we expect to get is stable fracture propagation, and so forth. So if we increase the density of the drilling mud even further, we've got further stable fracture propagation, and the fracture apertures are quasi-linear. This is actually quite interesting. So to summarize, these drilling-induced tensile fractures, they frequently inform strike-slip tectonic regimes. Initiation occurs when the tangential effective tensile stress exceeds the tensile strength of the host rock. And once initiated, you would expect initial sudden fracture propagation followed by stable propagation. So let's see what we get if we try to model this process numerically. This is the DEM model that I designed for studying drilling-induced tensile fractures. It's rigid blocks parallel to the borehole axis. I use periodic boundary conditions, so it's a plane strain model. The outer radius is 10 times the inner radius, and I used here refinement. I used very high resolution, 1 millimeter sized tetrahedral elements. The reason is because the stress gradients are very large in that area, as you will see later. I'm going to talk a little bit later about, how it generated a mesh and everything. So this is the geometry of the mesh and the model setup. So it's a hollow cylinder. Boundary conditions. I'm installing that regional stress using the R-block tractions command, and I also have tractions on the outer surface of the cylinder and obviously on the inner surface in the borehole. Yeah, and the tractions are computed based on a certain depth, certain density of the drilling mud, and I just apply that to the facets. So a close-up of that. So these are not tractions, they are forces, applied forces, and this is why they're much bigger here, because the facets are bigger here because of this refinement. But this is all with a model where a fracture has developed, and that's a close-up. So these are the broken bonds between these TETs, and I'm using the PFC fracture connectivity logic. Any fractures that are connected with the borehole are getting pressurized, so they get the same pressure as in the borehole. So let's go back why I had to go through this process of this local refinement and everything. As I said, it's the stress gradients that are very large, and this region where tensile stress is developed is actually really quite small. So this white contour here, this is the region where the least principal stress is actually tensile, and this is plotted here in a graph of the effective principal stresses as a function along the distance. And you can see you have very large stress gradients. So you really need a high resolution to capture that. And this is a model sliced through the middle, plotted here for the sigma YY normal stress component. And you can see that I'm really nicely capturing this stress perturbation. And then obviously you can take this model, without bond fracture, and then you can compare the secure solution. Well, of course, it's a DM model, it's TETs, you have a mass, 4 springs. Of course, you're going to get some scatter, but the comparison with secure solution is quite satisfactory. Right, so what do the fractures look like? So what I'm doing, I'm having this initial drilling mode density. That's a pretty much standard density that was used during the drilling campaign of Nagama 1100. The maximum is about 1,300. So I'm covering here the range that was used during of drilling mud density that was used during these drilling operations. And what you can see here, the fractures colored for aperture, the fractures do propagate. But it's a numerical model. We can analyze it in many different ways. We can unwrap it. We can have a synthetic borehole image log. And we see these classic centerline fractures. And we also can color it for effective circumferential stress. Now this is really cool because what is red here is tensile stresses, and you can see as the fractures propagate into the far field, you get a greater stress shadow around these fractures. What about the apertures? I'm plotting here the apertures as a function of distance. Compare it with the analytical solutions. And yes, there's a scatter, but in general, the agreement with the analytical solutions is really great. Right. So this was part was now about model validation. So we designed a routine to model drilling-induced fractures. We compared with analytical solutions. Now we can start really playing around with the tool. The reason why it's important to play around is that quite often you don't get a centerline fracture. Quite often you get stepping fractures, kind of Arch-Law arranged fractures. The different mechanisms, obviously, you can think about, well, the borehole is not aligned with one of the principal stress axes, or there's anisotropy, etc., etc. So what I'm going to show you now are a few models where I put in mechanical layering, and I systematically varied the dip direction of the layers in relation to the least principal stress direction, horizontal stress direction. And I just varied the Young's modulus of these layers by a factor of 2. So let's see what's going to happen. So first of all, the fractures nucleate first in the stiffer beds. And then when you increase the density of the drilling mud, they'll also develop in the compliant beds. And what you end up with are stepping fractures. Now, the far-field principal stresses are aligned with the borehole, yeah? But it's this mechanical layering that introduces stress refraction, and this is why you get stepping. So to summarize this part, we've developed a routine to model drilling-induced fractures, which was validated with analytical solution. And you can put in mechanical layering, and you get really quite complex fracture patterns, even though the far-field principal stresses are aligned with the borehole axis. The important thing is, why did we do it? The idea was to generate a library or an atlas of drilling-induced fractures under various conditions to better help people interpreting these things when they have them in the borehole image logs. Why is it so important? Because they tell you something about the present-day stress in the Earth's crust. And that's something important. What you need to know, for example, if you want to deposit radioactive waste, etc., etc. Right. So that was the first part of my talk. And now let's move to faults. I've been in a fault analysis group. I still work with faults. I love faults. Faults are fantastic. They're really interesting. But there can be troublemakers. Because as we know, if we change the present day conditions, poor changes of pore pressure, for example, let's say during geothermal energy operations, they might be reactivated. Yeah. And you don't want to, scare the people, basically that's it, So what is used traditionally is that you map out the faults in the subsurface. You know then the orientation of these, the local plane, the fault plane. You assume a certain stress state in the Earth's crust, and then you can work out what is called the slip tendency. Basically, you have a measure between 0 and 1 that tells you how close you are to the Coulomb slip condition. The problem is that you always assume locally that the fault is planar. Faults are not planar. Yeah, faults are irregular. They have corrugations, this waviness, and so, what's the friction coefficient of these faults? You can't really take the local friction. You have to take the friction coefficient of that irregular plane. And all of you, I'm sure, have heard of Patton's slip criteria, where Patton assumed you have a sawtooth profile with, periodic teeth, and then you can work out what is the effective or the bulk friction angle of such a fracture geometry, and it's simply the friction angle on that plane plus the inclination angle. It's a very simple relationship. Okay, so I could ask you, what's the friction angle of that fault? And it will obviously depend also on the orientation of the maximum resolved shear stress, yeah, because pattern only solved the problem in 2 dimensions. Right. So I thought, Jesus, I couldn't find anyone. Please tell me if I'm wrong, but I don't think anyone has solved this problem in 3 dimensions before. So I went along and said, okay, I'm going to solve pattern's problem in 3D. And I said, okay, I've got this simple sawtooth-shaped fault plane, and I'm having a direction of the maximum resolved shear stress on that irregular fault. What's the slip direction? And the interesting thing is that this geometry introduces an anisotropy. So the slip direction is generally not parallel to the direction of the maximum resolved shear stress. Right. Okay. Now I said, okay, I need to get an analytical solution for that, but I'm not smart enough for that. I need to model that, and the model will help me, will guide me to develop that analytical solution. And that's what I did. So I take this sawtooth geometry, I meshed it with Gmesh. It's an open source meshing software for tetrahedral elements. Took the geometry, imported it, converted it to griddle format, and imported it into PFC. Again, I use periodic boundaries, so my fault is an infinite sawtooth plane. And then, that's a cut, that's a section through the model. And I wanted to induce slip on that fault by changing the pore pressure. Yeah. Now, this is not really implemented in PFC yet, but you can do it. So I'm using the spring network model. Dave has already shown how you can use that. So I'm not going to go into the details, but this is the constitutive equation for pore elastic material. So this is the pore elastic part here with the pore pressure. Now what the spring network contact model is doing, it assigns stiffnesses to get a 0 Poisson ratio response, and then PFC computes these fictitious contact forces to do the PFC correction. So this part is implemented. So all you need to do is to account for this pore pressure changes. So you just have to modify the contact normal forces in order to get the desired pore elastic response. Yeah. So I increased the pore pressure in small increments until I couldn't solve anymore this model. Yeah. So I got unstable behavior, and then you get slip, and you get this formation of these pull aparts. So I did that for several different orientations of the maximum resolved shear stress. I then determined the friction angle, the effective friction angle, and also the slip direction. I'm not going to show you the equations. I haven't published them yet, but I can tell you that the analytical solution fits the PFC data really well. What's really interesting is there will be a critical angle of the maximum resolved shear stress when you start moving in the grooves. Yeah, you have this guided slip. That's what it's known. It's known as guided slip. Yeah, but the important thing is slip in general will not be parallel to the direction of maximum resolved shear stress. Right. So to summarize that, we've developed a scheme for modeling the reactivation of irregular faults due to pore pressure changes. Without that scheme, I don't think I could have arrived the analytical solutions. I also derived them for a cohesive fault. Jesus, that's a real pain, I have to say. But anyway, it's really great. I think PFC is a great tool and other numerical schemes developed by ITASCA to help you to derive analytical solutions for the problem at hand. The classic slip tendency that is used nowadays, be aware, might not be right, might give you the wrong answer because faults are irregular, And as I said before, this is expected that the slip direction is not parallel to the maximum resolved shear stress, which is important for geologists that do paleo stress determination, just as a side remark. Right, so gonna finish with a hot topic. Don't want to say it's a hobby, but it is kind of a hobby. Yeah, I'm collaborating with volcanologists, and we try to better understand the mechanics of calderas and caldera collapse specifically. What I'm showing you here is a small vent in Hawaii. That's a Pu'o cone in Hawaii, and on the map here, you can see it's east of Kilauea, of the Kilauea caldera. So it's a relatively small-ish caldera with a diameter of 300 meters. And that's active. That's for quite some time. And I'm going to show you now some images from the USGS that is showing that 2011 eruption. It's a Kamoa eruption. And the eruption was not at the volcano. It was a few kilometers away. Yeah? So this is what we call a fissure eruption. And you can see the magma is coming out there. And you have to imagine there's this connected network in the subsurface with a magma chamber. And quite often what happens is that the magma is propagating laterally and then extruding, further away from the volcano. And obviously at some point you get an underpressure in that magma chamber, and then the caldera collapses. Just to show you another image with a pretty brave geologist for scale, I have to say. And so this is the fissure eruption, and that was going on for a while until the caldera collapsed. And that was, geologically speaking, a super fast event. It was 115 meters of subsidence. And then my colleague on Houlihan, they had a camera installed. This is really the best documented collapse ever. Yeah? So there was a remote time-lapse camera installed, so they really could decipher in detail how this collapse occurred. It was, as I said, 150 meters in about 2 hours. Right. So the question is obviously, what is the underpressure? What sort of critical underpressure you're going to have to reach until that thing goes down. So with the student from Chile, there are many volcanoes in Chile, so I'm co-supervising him, and so we designed this rigid block model. I know it's two-dimensional, but let's stick to 2D first. I've got another student who's trying to do that in 3D, and that's obviously much more complicated. Right. So we've got the magma chamber here, and we just have initially there a magma static, you would call it, or lithostatic boundary condition. And then we decreasing, it's just applied forces to the facets of that magma chamber, and we slowly decreasing the pressure to see what happens. And an important thing is, what surprisingly no one has looked at before, are the effects of the regional stress field. Now, this can be nicely expressed as the Earth's pressure coefficient. I'm sure you all heard about it. So we assume we have a critically stressed crust that is in a Rankine state. So what my student did, he then systematically varied this Earth's pressure coefficient so that we could model an extensional setting like a normal faulting regime, or a compressional setting, a reverse faulting regime. We also looked at an isotropic stress. And then what you have here, these are curves of caldera floor subsidence as a function of the magma under pressure. And perhaps as expected, you can see that you have the onset of collapse occurs much earlier in the normal faulting regime than in a reverse faulting regime. So, to summarize that part, conditions for collapse are sensitive to the regional stress field, and the magma under pressure required for collapse increases with increasing Earth's pressure coefficient. This is ongoing work. I showed you here models for caldera collapse on virgin ground. We also want to put in fractures and pre-existing faults and have a look on how they affect the style of collapse. So to summarize, the rigid spring, I'm not doing balls modeling anymore. It's crazy. I'm only doing rigid block modeling now for quite some time, because it offers really a new avenue for investigating a wide range of geomechanical problems. The neat thing about the spring network model is that you have a perfect linear elastic response up to the point of fracture. So this really nicely allows you to compare your models with analytical solutions, be it linear elasticity, poor elasticity, linear elastic fracture mechanics, etc. And I really have to say, Matt, thank you so much, because without the development and constant support of Matt Purvins, I wouldn't have achieved what I've shown you today. Thank you. Ooh, that was quick.
Thank you, Martin. Wow, that was very quick. We got plenty of time. Let's ask him a bunch of questions. Who's up first? Go ahead.
In the amazing presentation, I got a lot of ideas. In the first part of the presentation, you were talking about linear elastic fracture mechanics.
Yeah.
And logically, it depends on the particle size. So then you modify certain part of the borehole you decrease the size of certain part of the borehole. And one of my questions is,
here we go.
Why did you? What would happen, with the results if you would be uniform throughout all the borehole? Why not to have the small size throughout all of the borehole, throughout all?
Okay.
And
Yeah, I know exactly what you mean. Okay, fracture toughness will depend on the size of the size of the rigid blocks, definitely. And in order to get close enough that you get the right ratio of tensile strength to fracture toughness, there's more or less a linear relationship between the two. Yeah, you have to get basically to the grain scale in terms of size. Yeah, so I got pretty realistic values for the tensile strength and the fracture toughness. But I can't use that size in the entire model. Yeah. So, and because I'm having conditions, boundary conditions and stress conditions that will lead to tensile fracturing, I only need to really have a high resolution in that areas where I expect the fractures to form. So everything else would be a waste of computational time. But this works only for that. So if you want to model borehole breakouts, they would develop in that area. Yeah, obviously, you have to have a different refinement regions and everything. Yeah.
And my other question is regarding the deformation moduli layers. How do you choose the thickness and the reduction of deformation modulus for the layers where you reduce the deformation modulus and you impose a thickness of that?
Here, I think the thickness here was 1 borehole diameter of the layers. Yeah. And I wanted to have it periodically layered. So it's an infinite stack of multi-layers because I use periodic boundary conditions. I picked that number because it's nice. Seriously. Yeah. Why not? It's a realistic, thickness of bedding, when you look at limestones. So many of these drilling-induced tensile fractures formed in Jurassic limestones, and they would have 10 centimeter, 15 centimeter thick beds. So it's perfectly realistic.
Thank you so much.
Yeah.
Other question. Here's your chance to ask a structural geologist your questions about. Well, then I'll ask a question. I always have a question. How is this type of work received in the structural geology community? Because you're doing it. I assume to them this is very exotic type of thing.
Yeah. Yeah, quite often when I present this stuff at geological conferences, people just shake their heads and switch off. Because they're scared of math and mechanics, which is sad.
So they're not just scared of PFC, but they're scared even of math and mechanics.
Okay. Yeah, so I had to, then I just would show some equation, people. So it's difficult, but not everyone is like that. I mean, that I'm getting more in the area of, reservoir geomechanics, and in that area, it's much more appreciated what I'm doing than kind of your standard geologist who likes fossils and minerals. It's a difficult audience.
Yeah, Jim.
Why tetrahedra instead of boronoids?
You've got fewer contacts per element. Very simple. It's simpler to generate the mesh. And yeah, you have a bit more scatter. Yeah, when you have a look at the Bursite, You get less scatter with Voronoi, but simply because you have more contacts per element. But what matters is the bulk behavior of that material. So I think that's fine. I've been discussing that a lot with Matt, and it's just a little bit more painful to generate Voronoi for more complex geometries. Having a conformal mesh when you have it's getting messy.
Is there another question right here? Yeah, go ahead.
So basically, very interested in your the sort of crack propagation analysis, and I did some work on that before. So usually, based on my understanding, there are two challenges for crack propagation analysis. First, for conventional finite element, first is it's very hard to capture the stress field at the crack tip because it's an asymptotic distribution, and the shape function of the conventional finite element is polynomial. So generally, you need a very fine mesh to capture the stress field at the crack tip. That's the first challenge. Second challenge is you need a regular remeshing, to model the crack propagation paths.
Yeah.
Right? And based on my understanding, there are no commercial code for crack propagation analysis due to this challenge. So in your analysis,
you're talking about finite elements.
Yeah, finite element, conventional finite element. Yeah. So in your analysis, you first address the first challenge is about the stress field. You use a fine element to capture the stress field. For the second, the challenge for the remeshing procedure. So you did not model the actual crack propagation path. You regularly remesh the mesh. You did.
No, I'm not remeshing.
Yeah. You basically, for your fine the mesh element, you predetermine a region of this crack propagation, right? The crack development.
Well, no, I'm just having a high resolution in the area where I expect the fractures to propagate, but there's nothing predefined. You can set the tensile strength of the bonds. What you can't set is the fracture toughness. The fracture toughness is an emergent behavior. Okay? So I haven't shown that here, but you can do, lab tests with pre-existing cracks, and determine like that the fracture toughness. This is with rigid block modeling, yeah. In Excite, the fracking basically tool of ITASCA, they developed a really neat method based on the J integral around the fracture tip, and then you can determine, okay, does the fracture propagate or not? So you can set the fracture toughness there, but you still have to integrate around the tips, yeah, to get the stress intensity factor. I'm not doing that because, I've got a fracture toughness, which is quite realistic because I'm doing grayscale modeling, basically.
Okay, so the crack usually structure design and those dam comfort erosion is all depend on the crack weight, and this people usually want to analyze this crack in more detail.
Well, I could imagine that you could design a rigid block model that looks at locations of cracking, and then ahead of the crack tip, you take the rigid block and you refine that. Yeah. So you would have dynamic refinement during fracture propagation. I think that could be quite easily done. Yeah. But for fractures, you want to use TEM for fractures, really?
So he doesn't need to do remeshing, right? Because the cracks can only go along the edges of the.
Yeah, but another question is, what's your crack propagation criteria? So,
bond strength. It's local bond. It's a local criteria for the bond strength. It's just bond breakage.
Yeah, it's the. For example, in your the toughness is actually not the stress based. It's sort of energy based. Because your toughness, the unit in toughness, it's not like the stress unit. It's a km times meter, like the normalized by characteristic length of the material. So usually the stress criteria is not very good for crack because the crack, you can see at crack tip, the stress field is very asymptotic. So some people think the energy-based criteria is better for crack propagation. So they have the different criteria to for crack propagation. Yeah, that's based on my understanding, that's a bit complex, like the criteria.
So I'm going to jump in. You got. Let's talk afterwards because that question is being addressed properly. With this work. What? 2 more minutes. Any questions? Comments? Okay. All right. Well, let's thank our speaker, Martin. Very nice.